So this is our then final lecture on regenerative or vapor power cycles. We covered regenerative vapor power cycles. It's where you have an open or a closed feed water heater. The key idea is to have feed water heaters. This isn't much of a feed water heater, is it? It's basically you just mix the two streams. There's not a whole lot of design. It's actually just mix the streams, okay? Here you have shell and tube heat exchangers. And I'll show some pictures and we'll talk a little more about them. But we incorporate the closed or the open feed water heater into an actual power plant. This is a problem that I set up last time and kind of breezed through. True? I showed the schematic and I showed the solution to it. One thing I wanted to do was make sure that you're able to develop an equation for how much of that steam is diverted to feed both of these feed water heaters. So do a mass balance, maybe I should be a little clearer right in here, cutting through state 10, and an energy balance for that calculation of Y1. So in order to do that, Rel, you need to know what Y1 is. What is it defined as? The mass flow rate that goes to feed the closed feed water heater divided by the mass flow rate that goes through the first turbine stage. All right. So what we do is you start with the mass flow rate that goes into the first turbine, then it comes out, then some is split. So this is the mass flow rate that goes to feed the closed feed water heater. And then what is this up here? This is the mass flow rate turbine 1 minus the mass flow rate of the closed feed water heater. And you work your way around, okay? So if I took what continues in the loop and I divided it by m dot T1, it would be 1 minus Y1, wouldn't it? So we use that abstract syntax. Oh, the mass fraction that goes down is Y1. 1 minus Y1 continues. So what goes into the first or the second turbine? 1 minus Y1. But what happens here is we have Y2 is being diverted away. There's two choices for the definition of Y2. It could be the mass flow rate that goes and feeds that open feed water heater. Both of the definitions will have that in the numerator. But either you divide by the mass flow rate that went through the second turbine, or you divide by the mass flow rate that went through the first turbine stage. They're not the same definition of Y2. Which definition of Y2 is used in the book and is most convenient for us? The second one. So this is the preferred definition of Y2. Because that's the definition of Y2, the mass flow rate that continues to go back for reheat and then goes into the third turbine is what came out of the first turbine stage minus what went down to feed the closed feed water heater, minus what went down to feed the open feed water heater. Isn't that what continues through the third turbine and through the condenser? And if I took that equation and I divided, or that mass flow rate, divided by the mass flow rate through the first turbine, it would be 1 minus Y1 minus Y2. It's a real simple expression for what is the mass flow rate through the third turbine and through the condenser, etc. All right.
What side of the equation should it be an m dot simple y?
Yeah, that's m dot. Thank you very much. And now we can do our mass flow rates. So Y1 is what goes into this closed feed water, and what comes out over here is Y1. And then what goes into the open feed water heater from the bottom, Y1. What comes in from the top, Y2. What comes in from this pump, 1 minus Y1 minus Y2. So what goes out to the second pump? 1. And then 1, and then 1. So we get our mass balances. Now let's get our equation for what is Y1. So this is the correct one, this is the incorrect. All right. So when we do an energy balance right here for that closed feed water heater, we have the H2 times Y1 that's coming in, And we have minus H12 times Y1. That's what's going out, so we put a minus sign on the energy balance. And notice that we could just combine those because both of them are multiplying Y1, so it's H2 minus H12 times Y1. It's really what comes out of that stream. Where does it go? It goes into the other fluid stream, which is H11 minus H10 times 1. And so there's our equation for Y1. H11 minus H10 divided by H2 minus H12. Be careful, go slow, have confidence in your work, do it right. Did I do it right? Good? All right, how about now for the energy balance to get Y2? Well, same thing. You got your mass balances, so what comes in is going to be H4 times Y2. And in from the bottom, H13 times Y1. That's a Y1. And then what comes in from after the pump, H8 times 1 minus Y1 minus Y2. And the only out is 1 times H9. What did we know about state 7 and state 9? Both of them are saturated liquids. Okay, so you can rearrange this to solve for Y2. All right, it's algebra to get the Y2. On the next slide, I have the equation for Y2, and I'm running out of room. So, ready to go on? One other thing. What about state 11? Is it saturated liquid coming out? Two-phase liquid vapor? Compressed liquid? It's compressed liquid. It's compressed liquid. You have to, that's usually given as part of the problem statement. Okay? All right. So, here is the equation that I promised for Y2. Notice that Y2 is a function of the H's plus I left in Y1. You could take the equation for Y1 and substitute and then have Y2 as a function only of H's, but it makes a longer equation. True? Okay. So for this problem, we already know that, what's that? Nearly 17% and 8% are the mass fractions that are diverted. I covered this. This is the key equation or the key data. You need those enthalpies so you can get the Q's and the W's for each component. Get them all on a per unit mass basis entering the first turbine, and then calculate the back work and the thermal efficiency of the cycle. Is there any questions about this? Yes?
Are you not able to calculate S for like state 9?
Some of it, it's not.
Some of them you left blank.
Some of them, they're not needed because once I was able to get the H's, I wanted to move forward. Some of them, they're a little tricky in the sense of getting that, because right here is I basically have the pressure plus the enthalpy. If I wanted to S, I have to be able to get S as a function of pressure and enthalpy.
Yeah, it's on the homework it said find all of them.
I know.
Sure how to
It's a little challenging, isn't it? How would you find this S right here? Yeah, but it's going to be a compressed liquid at state 8. It's after a pump. Okay, what equation did I use to get this number right here? The pump work, which was VDP. As long as it's just the pump work is VDP, embedded in that equation is that it's reversible pump. So guess what S is? The same. Right?
How do you figure out the H coming out of the closed feed quantity?
This H coming out of the closed feed water heater, two things. You could look it up as a function of pressure and temperature in the compressed liquid table. All right? If you don't have much interpolation, that's a really good number. especially if it lands on a point in the data, in the table. Otherwise, basically, get H11 is an approximately HF at that temperature of 11, ignoring the effect of pressure.
And I did it both ways now.
Minor differences. Now, if you get where you have to interpolate or double interpolate and it's far away from a data point in the table, it's more error prone than interpolation. So use the simpler approximation, especially if you wanted to get the H of 10. How many people did the H of 10 because you knew the pressure and you knew the entropy, and then you found the work of the pump using that way? But you found that it's a lot different than using VDP. True? Did you try both ways? It's a lot different. And so what it is we're linearly interpolating. And if you're kind of in no man's land in the table, far away from pressure and far away from temperature, your interpolation isn't that good. So it's actually better to know it's isentropic. That's my assumption. It's isentropic flow through the pump. And so the work, the minimum work, is VDP. Right? So I've just kind of given you a hint. You can pretty much avoid using the compressed liquid tables. It's a lot faster without needing to do a double interpolation. Well, I've avoided it up to this point, but I don't want to avoid it anymore. What happens if there's an isentropic efficiency for the first turbine, isentropic efficiency for the second turbine, isentropic efficiency for the third turbine, isentropic efficiency for the first pump, and an isentropic efficiency for the second pump? It's not anything new in this chapter. It's all the tools that you learned in Thermo 1. Right? That's all it is. But it makes the problem a lot longer. I could hear the groaning. So basically, you need to be able to do that for the exam. It's fair warning. Very good. You have them all, Mason? All right, very good. And basically, let me do a quick reminder on one of the turbines, right? So what I do in the table is if I'm going to analyze this turbine, the first turbine, I'm going to think about expanding conceptually to state 2S and then expand it to state 2 actual. So I'm going to have two lines, multiple steps in the calculation. So I'll expand it to 2S. That's exactly what you've done already. No difference there. It's now that I have H2S and I have the work that is out of the first turbine, which is H1 minus H2S, and the isentropic efficiency says, no, you didn't get that much work out. This is, you could think of that isentropic workout. Work of the first turbine actual is the isentropic efficiency of that first turbine times the work if it would have been isentropic expansion. Isn't that the use of the efficiency? And so now I can get the actual H2 actual H2 actual is going to be H1 minus the work of the turbine 1 actual, which you could expand to say H1 minus isentropic efficiency of the first turbine times H1 minus H2 isentropic. So for each one of those exit states, I'll have 2 steps. And I'll usually talk about 4S and 4 actual. I'll talk about 6S and 6 actual. I'll talk about 8S and 8 actual. And 10S and 10 actual. For the pump, you just have to remember, it's not that we get less work out of the pump. No, we have to put more work in. So let's take a look at the equation for 8. So we had 8 here. I'm just going to try and tuck it in down here. We had the work for pump 1 isentropic was V of 7 times P8 minus P7. True? All right. What is the work pump 1 actual? That divided by the efficiency, not multiplied by the isentropic efficiency, isn't it? So it's going to be WP1 isentropic divided by the isentropic efficiency of pump 1. So that's the only key right there. And so you get that H, let's say 8 actual is going to be H7 plus that WP1 actual. That look good? Makes the problems a little longer. One other thing I forgot to emphasize is somebody says, how do you get H13? It's the same as 12. You've done an analysis of a throttling valve, and so it's no heat transfer, no work transfer in or out of control volume around. It's isenthalpic. All right. Now, once you have all these states, let me show you here the extra calculation. I tried to color code green and green and green and green and green, right? So those are for the first turbine, second turbine, third turbine, pump 1, pump 2. That's the additional. These are some efficiencies to modify, change up the problem. It does not improve the overall thermal efficiency of the plant. It degrades it, as you might expect. Not much of a effect on the back work ratio. It does have an effect on the back work ratio, though, a little bit. And I already talked about all of those steps. Somebody asked a question about S's. Now, this S would be a little harder to get, wouldn't it? Yeah, because let's say going from 7 to 8 isentropic, well, that's the same S right there. But at 8 actual, I really do have to look it up as a function of pressure and enthalpy. And that may be difficult to do, get S as a function of pressure and enthalpy. All right. All right, let's press forward. We want to be able to plot it on a TS diagram. You may or may not be given a page for the TS diagram. You may have to sketch your TS diagram. But if you do, I would encourage you to find your pressure lines. For that pressure, it was 8 megapascal. It was 2 megapascal. It was 300 kilopascal, somewhere between 5 and 200. And then 20 kilopascal, right? So knowing that those are the pressure lines, you can find all of your states on that diagram. Can you? So if we come in at 440 at 8 megapascal, we expand it down to 2 megapascal. But if it's irreversible, we don't use a straight, a solid line. We use a dashed line, and the entropy is going to go up. And it probably is going to come out superheated vapor if it wasn't already superheated vapor. Reheat to some point, expand, but then if it's irreversible, go over like that, some line, then reheat, then isentropic expansion, or if there's irreversibilities, depending on, it could still be two-phase or it could be slightly superheated. It all depends. And then condense. After the condenser, you put it to a pump. There's the pump. Where is the actual out of the pump? The itty-bitty bit to the right. That's right, right there. And so it's on the same pressure line, but a slightly higher value of S. Very slightly higher value of S. Okay? This one is challenging in the sense of where is, so we come out with 8, where is state 9 on that TS diagram? 9. Saturated liquid at what pressure? At the open feed water, which was 0.3, so it's right around here. Right? Around 300 kilopascal, right there. Put it through the pump, little irreversibility of the pump. I mean, you have to get a magnifying glass to see the difference in those points, right? All right, now let's jump back. So we got 9 and 10. Where is state 11? What was the pressure at 11? 8 megapascal. What was the temperature at 11? 210 degrees C. True? And then once I find 11, then I want to find 12, okay? And then 13. So let me not jump back and forth. I'm going to find 11, 12, and 13. Okay, so where is 11? High pressure at that temperature of just a little bit over 200. So it lands right in there. Isn't that 11? Now, where was 12? Saturated liquid at the 2 megapascal, which is right there, slightly lower temperature, right? Isn't it saturated liquid at that 2 megapascal? So right there is 12. Hold it, was that 11 or 12? Oh, I forgot my numbering system. There's 11, saturated liquid coming out at the 2 megapascal. 13 is the next one. Where is 13? That's right. So it'll be irreversible expansion through that throttling valve. So S is going to increase going from 12 to 13, and you're dropping to the lower pressure. So it'll be somewhere like that. It's at that 300 kilopascal pressure, isn't it? So we'd like to put a dashed line in there. It's not straight down. It's over a little bit to the right. Makes sense? We're done with that. Let me hit a couple topics. Sometimes you'll see this term, organic Rankine cycle. Well, what's that mean? Basically, instead of water, which is an excellent working fluid, you use some sort of organic compound or substance. A good one is a refrigerant, because it has, just like if you studied organic chemistry, it has carbon in it. Does water have carbon in it? No. It's not an organic fluid, right? So, but if you have refrigerants, they typically have some carbon, so they're organic fluids. They're typically higher molecular mass fluids. And why do we choose to use them? Because we may not have a high temperature heat source, especially if you're trying to develop power out of a low temperature heat source, geothermal, or some other burning trash or something. You want to use a lower something that boils at a lower temperature. So you'll see that term, organic Rankine cycle. All right, binary vapor power cycle. Well, maybe you have something that's super hot, and maybe you can use a fluid that would be at that high temperature to take in the heat in the boiler at some super high temperature. Here's one, it's mercury. So that's going to boil at some very high temperatures right up here. And then, but it's still hot when you're ready to condense. Put it through a heat exchanger, which is a boiler for another fluid that boils at a lower temperature. Here they're using steam. But often what they'll have is they'll have water on top of some refrigerant, some organic fluid. So you could try to extract more out of it. It's tricky to really extract a whole lot more out of it. It's not that there's no magic wand to turn a vapor power cycle into super high efficiency. It's usually down there in the details where the engineer makes his money or her money, whatever. They have to work on better pumps, better turbines, better heat exchangers, and fine-tuning and controlling the operation of each device so it doesn't go off from its desired operating point. Cogeneration is another term. We don't see a lot of it in Texas, but if you're making electricity but you have some warm steam, maybe you divert some of that steam to heat buildings in the middle of winter. Our summer lasts 8 months, 9 months. Some people's winter lasts 8, 9 months, right? So this is more popular up north. We have not a heating district in San Antonio. We actually have a central chilled water loop in downtown San Antonio. It's run by SAWS, and it provides chilled water to the Alamo Dome, a lot of the big hotels in that downtown area, and they have 2 main plants to make the chilled water. For a number of years, they also had a steam loop, and the same group sold steam and they sold chilled water. But they did the books and they found out they were losing so much money on the steam, they cut it. So they just do chilled water. Carbon capture and storage. I think you're going to see more of this that engineers have to deal with. What are we going to do about the CO2 emissions in power plants? You already see that in the economics and stuff with the coal. Nobody's building a new coal power plant now. About 5 to 10 years ago that changed, especially with the price of natural gas. But the carbon dioxide is going to be a challenge, and I used to think that it wouldn't be much of a challenge, but the more I look at it, it's going to be more of a challenge for you in your 40 or 50-year career in engineering, right? So one of the strategies is to try and capture it out of the emissions waste stream and do something useful with it. One of it would be to throw it down into the ground, sequester, or put it down where it can actually do something useful. They had it planned in West Texas to stimulate depleted oil wells by CO2 emissions. That was on the books. City of San Antonio, through CPS Energy, bought into the project, said they were going to fund it. They're actually going to buy half of the power out of it, which was a big financial commitment from the City of San Antonio, which are you, the ratepayers and all that. But then the fracking happened and the price of natural gas dropped. The project was quasi-experimental. Remember when Obama was elected president, there was a stimulus package? They got, I forget how many million, couple $100 million for that project in West Texas. But then things faltered, people pulled, CPS pulled on it. They didn't renew their option to stay in when it expired. But I think you'll see some more of that coming in the future, where they'll try and capture CO2 and do something instead of just putting it into the atmosphere. Clean coal, for a while that was a buzzword. You can burn and have clean coal. The problem with coal is it's just a lot of carbon. And so you break carbon bonds, so you're going to make CO2. If you take a look at it, methane is cleaner burning because of the 4 H's. And so you're breaking the H and the C bonds. And that liberates a lot of energy with less production of CO2 per BTU or per kilojoule of heat release. But anyway, a lot of work for mechanical engineers in having clean coal-fired power plants. A lot of technology. The integrated gasification combined cycle plant, that was actually what was going to be built in West Texas, CPS funded or engaged in, and they were going to then capture the CO2 and put it down to stimulate oil wells. This one's interesting because you're going to burn coal, but the way you're going to burn it, you're going to pulverize it, mix it, and turn it into a synthetic gas like natural gas. In that form, it was a little easier to clean it, get out of the mercury and sulfur and any other ash type things, and then it was a little easier to have clean emissions. So anyway, you'll see a lot of these terms kicked around. Now let's talk about feed water heaters. If you just Google it and read, it's exactly what we're talking about, have talked about. Preheating the feed water to reduce the irreversibilities involved in steam generation and improve the thermodynamic efficiency of the system. You can look at sites where they're actually sponsors or selling these. They put out a lot of information. Here's a blow up. And I know that they're just heat exchangers, but there's a lot going on and a lot of engineering in even the smallest detail of these heat exchangers. So you bring in some steam, and you're going to have it go in this direction for flow through the device. And when it's in this region, flowing that way, you first de-superheat the steam. That's where the temperature's the highest. Then it moves into a condensate where it's condensing region, so it's a condensing zone. And then it moves into a subcooling zone. And what comes out is liquid from that feed water heater. This is a closed feed water heater. Somebody said, why don't they have a nice illustration of an open feed water heater? It's two pipes, and you put them together. It's mixing, right? Not much in there. But here's a shell and tube. And you can see that they bring in the feed water. At first, it's going to be really cold, and so it gets heat from the liquid when it's the coldest in that subcooling zone. Then it's going to get, when it comes out, the region that it sees right before it comes out is where the steam is the highest temperature. That makes sense. You really want this to be highest temperature possible coming out. So anyway, I thought I'd show you these. How long would it be? I don't know. Maybe the length of this room. Some of them in big power plants. Some of them be a lot smaller. Depends on the size. Also wanted to show a little bit about steam traps. There's a lot of different types of steam traps, but the idea is to discharge the condensate and any non-condensables because air gets in there. In our power plant, all our analysis, it's pure water. No air in there. But when air gets in there, air doesn't change phase, condense and all that, and it ends up accumulating in certain spots. And where it accumulates, you've got to get it out of there. So they'll have blowdown processes, or they'll have this steam trap, which will have two areas to let the liquid through, and then also a mechanism to get the air out. Okay. But this is an interesting term. Without the consumption or the loss of live steam. What are they talking about? That's an interesting phrase. It's kicked around quite a bit. But live steam means it's under high pressure. So anything above 15 psi atmospheric pressure is live steam. You don't want that to go through. All right, so they're basically automatic valves. There's a bunch of different shapes. And so what I wanted to do was to pop over. I would encourage you, there's not enough time to look at some of these things, but I have a couple video clips pulled up on YouTube. Let's take a look at some of them. So first of all, let me see if this plays.
Over half of First Energy's electricity is produced by using coal, compared to about 60% nationals on environmental protection.
That's enough of that one. So now let's talk about steam traps. Here's a video on testing the steam traps using ultrasound. It's about 3 minutes, so I'll take it about 2 minutes and then we'll stop.
Everyone's steam system has room for improvement. Industrial processes like food plants, paper mills, power gens, and refineries need clean sonic detectors.
So it's interesting that the one that fails closed produces possibility of water hammers in your piping system because the condensate's not getting out. You got more condensate flowing in pipes. The steam is flowing over it, creates a wave. Once you suck up a wave, it captures it, now it pushes it, and now you got a slug of high density material waiting for a turn. And when it turns, it hits an elbow or something, boom. Anybody ever experienced water hammers, been in a building where they have them? How about in a house, in the faucet, you just turn it off abruptly and you hear the anybody that? Yeah. Well, the same thing, but that's just a pure water system. But in steam systems, it's pretty intense. It's actually like a maniac with a whatever 12-pound sledgehammer banging on pipes somewhere in the facility. Just whang. That's what it sounds like. Here's some other videos that are really, really good. We just don't have time to see them and show them in class. But this is an inverted bucket design. They have multiple designs, floats, balls, and float designs. This is an interesting video. We're going to move and talk about gas power cycles next chapter. But this is a heat recovery steam generator unit in a gas cycle. Down here in this corner is a gas turbine, and the exhaust from the gas turbine to make electricity goes into this heat recovery system, and CPS owns a few of these now. And so let me just play this because I thought it was pretty good video.
Main or high pressure steam for the Mitsubishi steam turbine and directed to 2 discharge pipes on the bottom of the turbine casing. At this point, the steam becomes known as cold reheat. The 2 cold reheat lines, which are actually 2 high pressure steam exhaust pipes,
they actually put
merge
out
into
good
one
videos, but you have to purchase them, so they're for sale. All right. This is our chapter. It's the simplest, most straightforward chapter for the whole semester. We're not going to do any exegetic analysis for the exam. It's pretty much, especially the regenerative vapor power cycle, superheat, reheat, and the comparison between the ideal Rankine and the Carnot, and why we do things. Why does a power plant do these things? So with that, we'll see you here in this room Wednesday for the exam.